Good morning, everyone. Welcome to today's session. We are in the last week of lectures. This week goes by different names. This is the last week of April. It's the last week before we get to finals. It's the week 6 since we started doing things online. It's 10:10 here in Pullman, Washington, where I am, and I hope you are all well and have had a good weekend. It's a bit cloudy today, and I think it is probably the case for most of you. We will continue discussing what we started last time, but there is also one more thing I would like to do today, and that's to give feedback on homework 6, which James has completed grading, and I will incorporate feedback on that one into today's discussion. And so let me get started, and before we get to today's business, I just want us to see what we'll be doing this week. An agenda, and I have talked about this one a while back, and this is a week where we will minimize on number of new things we do, but rather use the time to look back and wrap up and then welcome the final exam. That's the agenda. So today we will complete the discussion we started around complexity theory, and I will talk about something called NP-completeness, and that would wrap up the discussion on time complexity. And it will actually be a way to finish the discussion we started last time, where we ended with one big open question, $1 million question. Actually, there is a prize for it. And then I told you nobody knows the answer. And so we're going to get something a little more positive around it. And so we'll have something that will make us make progress towards that, or what we know in terms of a positive direction in that open question. That will be the new thing we'll do. The portion of the class discussion today will be spent on getting a feedback on homework 6. And the reason for it is because it is completed in terms of grading. And if you've checked Oswald, and if you've seen this title today and you were intrigued by it, then you might have already seen that, but we will take a look at that one. But that one would require us talk about a little bit on how we are talking about homework 6 right now. And so for that reason, I will spend a little bit of time looking back and on all the homeworks and what's left. Wednesday's class will be the day where we'll review the course. We'll review the course in terms of preparation for the final exam, but also see what topics we covered. And that will be a lecture you would want to have in place. Friday will be the last day of lecture. That will be May 1st. And that's the day when I will introduce the final exam and release it. We do have a precedent for this. We know what to do with take-home exams. Our final exam is going to be a take-home exam. And so we have seen how this works in midterm 2. And so you know exactly what I mean when I say introduce and release the exam. And so that will happen on the last day of lecture on Friday. It's going to be a discussion around that, clarification and things like that. This is the agenda for this week. And we're going to get started with today's and why we are talking about homework 6. I'm going to walk through this one a little bit. And while I do that, because you are joining and a good number of you are already online, while I talk about this one, I want you to tell me something. I always ask warm-up questions. So the warm-up question today is starting on slide number 3. So it's a little bit delayed, but it is, I think, a good one. So I think now everybody has come. I'll talk about these ones, and you are looking at it right now. But the warm-up question I have for today is an extremely simple one and random. The question I have is, I would like to know what your favorite ice cream topping is. Last time when we talked about midterm 2 results, and I told you I was happy with how you did, I have encouraged you to get an ice cream that day. I'm not sure you did, whether you did or not, but that was one of the suggestions. Beverage was another suggestion. But if I were to ask you what your favorite ice cream topping is, what would it be? Go ahead, participate on the group chat session and tell me your favorite ice cream topping. This one is not going to require a lot of thinking like the ones we have been having around what comes to mind when you hear complexity, or what does philosophy bring to mind, or do you think this would be, solved using Turing machines and things like that? That kind of thing requires a little bit of thinking. This one doesn't, I think, unless you've got multiple favorites and you have a hard time picking one from another. But let me know what your favorite ice cream topping is. Okay, while you do that, let me walk through this slide and talk about why we are talking about homework 6 at this point. So we do have, this is an overview of all the things you do, basically. You have to complete this course and to have mastery on it and to show it to me and to the rest of the world, the way the syllabus was set up, we were to do 8 homeworks, 2 midterms, and a final exam. And this is how we have done so far and what we are left to do. We have, of course, this being the final week of lectures, done the majority of the work. But I think there is a very natural way in which things were broken down for us. So I like to think of this one as pre-spring break and post-spring break. The post-spring break is also coincided with how things transitioned into being online. But it was more or less midway. So before we got to spring break, which happened the last day, was Friday, March 13, was the last day before spring break. Or you could call that Friday, the first day of spring break, depending on how you want to count things. What we did then was complete the first 5 homeworks, and we did midterm 2. The way things were planned, all of these things were, and when things were in person. And so we did 5 of the 8 homeworks and 1 of the midterms. That was behind us. That was in our bags when we complete that. Post spring break, we had 3 homeworks. We planned to have 3, and we have had 3. And we had our midterm, and the final is yet to come. So in what is now listed under post spring break, I also wanted to think back and see when things were out and in, just so you know. And I think this will be also in some ways a preparation for your review on Wednesday and your preparation for your final exam, and to know where things are and which homeworks dealt with what sort of topics. So homework 6 went out on March 27 and it went in on April 3rd, and that was the homework we had, the first homework we had after spring break, and it had topics on context-free language and Turing machines. And after homework 6 actually came midterm 2, and midterm 2 did do things that were covered by homework 6 and a little bit of things that happened before spring break, and we did that take home. It went out on a Friday, April 10th, and you did this within 24 hours on a weekend on April 11th. You did your midterm to submit it in. And then came homework 7. It was out on 15th and it was in on the 24th, and the topics it covered were around Turing machines and decidability. And so decidability will be the 4th chapter in the book if you go by the way that things are organized in the book. And so we had that one. That was homework 7. And if you are now aware of where we are on Monday, April 27th, and this Friday that I'm talking about is just the Friday that has passed. And so you just turned in what homework 7 was, and you did do Turing machines and decidability type of problems that were roughly distributed around a little bit towards decidability, more problems, I guess. And so the very last question was Magic the Gathering, that game, and the other 5 problems were some other things. And so this is what we did with homework 7. We have had this tradition of having things in and out. And so the last Friday was also a day where homework 8 went out. And so we did have that one. And I am hoping that at least some of you were able to take a look at it this weekend. I know some of you might even have started with it. And this will be due the Friday that's coming. And that's the day when the semester concludes in terms of instructions. That's the day when we will have our final exam introduced, right? But that day will be a turning in of homework 8. And that homework had decidability, reducibility, and a couple problems on the very last topic that we are doing now on time complexity. There are only 2 problems on that. The other 4 problems are on decidability and reducibility. You've picked the pattern by now. Every homework had 6 problems. And so this was no exception. There were 6 problems on it. Sometimes things are weighed equally, sometimes they are not. Because it's yet to be submitted, I want to encourage you to take care of homework 8 as early as possible. Many things could happen this week. Fortunately, there aren't any new things that are assigned to you, at least traditionally, that's how it should be. And so I'm hoping that you will be able to take care of this one and actually don't have to wait until Friday to turn it in. So consider, for example, getting it done by Wednesday or Thursday, so you have it behind you, and so you've got all 8 homeworks. But that's what you have, and that's what we are in. Because homework midterm 2 happened on that, April 10th and 11th, and we wanted to prioritize grading that one. That was where we spent more of our time and James' time. And so homework 6's grading got delayed. But you've had the solutions. You've had the solutions for a long time because we wanted you to get ready for midterm 2, but it was there. You had submitted it like 2 or 3 weeks ago, and so you might have forgotten a little bit about it. Homework 7 is very fresh in your mind. You just submitted it. And so because the solutions were there, I was not too worried, but it will be a good idea for you to get some feedback. And that's why that's one of the reasons why it is included now. So you know what the time was, you know why we are doing it now, and you know what you have done with homework 7. Just as a matter of planning now, James and I are going to do everything we can to see, James, I should say, to see if homework 7 would be graded and you get feedback on it before we complete the semester. That means Wednesday is what we're hoping. If it happens on Wednesday, great. If not, it will most likely happen Friday, and so you will have feedback and solution for that one also. And so then you will have at least the first 7 homeworks gotten with the in addition to feedback, also the solutions, which will be one of the best ways in which you will prepare for the final exam. That will be released on Friday. The current thinking I have, and I think now it's not any more thinking, is the final exam will have the entire weekend for you. And so you will work on it the weekend, and on Monday, we'll decide the time, will be the day when you will submit it. But that will wait until we get to discuss it, and that we have also Wednesday to review the class and set ourselves up for what the final exam would be. So this is where we are. We are now going to be getting, or you are going to getting feedback on homework 6. And that's where this discussion will start. So just as a reminder, here are the questions that were there in homework 6. And James has done an excellent job in terms of all of the homework so far in giving you feedbacks that are relatively detailed. So for every single student, for every single problem, wherever there was something that was made that was not quite right or something, then you would get feedback that would tell you what the problem was or tell you how to better solve it and things like that. So it was not just relying on the solutions that we post afterwards, but you did get something. This time it could have been a little terser than other times. And so that's one of the reasons why it will be a good idea to get the feedbacks collectively now. And so these were the problems, the 6 problems. The first problem had to do to convert a context-free grammar into push-down automaton. The second problem had to do with converting a context-free grammar into Chomsky normal form. The third problem had to do with showing a language that's not context-free, and then that would be pumping lemma, use of pumping lemma. Problem 4 was on using the table filling algorithm to minimize states in it. I know this had been a long time, right? This discussion on how to use a table filling algorithm to minimize states in a DFA happened on March 13. That was a long time ago. But this is one of the reasons why it is a good time to think of it now, at least remember the names and where they were located, because the finals is coming and because you are at a point where you know all the contents of the course and there are places where you would want to be hearing about things repeatedly. And so I know it has been a while, but it's exactly actually a good reason why it will be good to think about them and talk about them now. So that was problem number 4, table filling algorithm to minimize states in DFA. Problem 5 and 6 were on Turing machines. One of them asked you to give an informal description and the other one asked you to give a state diagram. These were the questions, and if we need to say more about the questions or what the problems were, we will. This is one slide I have on observations made, and this is what I mean by feedback on your submissions and some of the frequently made mistakes that or James observed. And so this is a slide I put together based on what James had sent me, but were things that I probably are stated a little bit more in a shorter version to fit into one slide. So what I would like to do is, there are some of you who have had no problem, and most of the problems were some things that you either get full credit on or very close to full credit, and so probably there isn't too much of a point in having to hear a whole lot. And there were a good number of you on one or more problems where there were certain things that you made mistakes and things like that. So this is how the class looks like in terms of how they did in each of the problems and what stood out as things that are worth pointing out a bit and worth pointing out mistakes so that they are not made again in any time. Like if a question like this was to have to come or to an exam, or you've gone forward and you're moving on to other courses and other things, but then the time comes when somebody asks you for help on a problem like this, you know exactly what to do or how to answer to them. And so you should know what the mistakes were so you will avoid them, right? So that's the goal of this slide. So I'm not going to be reading them. So what I would probably do is just kind of paraphrase them, talk about them, and maybe if there are people who have questions would ask. But I'm going to ask, after I say a word or two about this, ask James if there are more things that have come his way later on, or if there are things that need elaboration. Okay, problem one was, this is the problem where we had to convert context-free grammar to push-down automata. And so the way this turned out, this was mostly fine by many people, and then some people might have forgotten one or two rules is the general takeaway here. But converting context-free grammar to push-down automata, I think that what was, yes, is what it was okay for most people. I'm reading at the exact prompts here, and so that is right. That was conversion to PDA. That was okay. The second problem had to do to convert to Chomsky normal form, the CNF form. And this is where things were not as nice as they were in problem one. Some people have done it kind of halfway, and there were they didn't, a couple unit rules were not removed, or there were some rules in the form A to B, C, and so that was a mix-up of terminal and non-terminal, which is what you shouldn't be doing when things are in CNF form, or there were things like A to B to C to D, which is when you have non-terminals that are more than, what you have on the right should not be of this type, but some people left some of these, I think, is what the general observation was. So I want to make sure that everybody now knows, after seeing this and after seeing the solution and after seeing one or two examples that we have done through the homeworks and through the lectures, that anybody who has made a mistake on this one would know next time they're asked to correctly convert to CNF form. I guess let me finish my run through this, and then I will ask James to chime in and see if there are things that he wants to elaborate on.
All right, I will, by the way.
Sorry?
I will have a few things to add.
Okay, perfect. So do you want me to first finish all this run through of I think it'd probably be better if you start adding, or do you want me to when do you want to add?
Actually, I could go through the entire thing if you'd want.
Oh, that would be perfect. So why don't you go ahead and redo this and paraphrase any way you wish.
Okay, problem one, I should probably add something I'd seen when I'd gotten a bit later through grading these.
Okay.
That I noticed that some of you would like to provide push-down automatas in the form of a bunch of transition rules instead of giving like a diagram, which is fine. But then I'd noticed that you'd only have one state. Like you'd write Q1 a bunch of times or Q0 a bunch of times. And I'm like, okay, so if you have only one state in your push-down automata, then either everything's being accepted because that's an accepting state, or nothing's being accepted. So that doesn't quite work for a push-down automata. Otherwise, anybody who attempted the general strategy for converting CFG to PDA, which has one looping state that leads to an accepting state and a state that pushes in the stack symbol and the entry symbol to go into that. Probably got mostly full credit or full credit. Problem 2, I did see a bunch more people who did not seem to understand that Chomsky normal form has only 2 types of valid rules, and that is one non-terminal mapping to 2 non-terminals, or one non-terminal mapping to 1 terminal. And anything else is pretty much not allowed unless it's the start symbol to epsilon. But that's a special case. Problem 3, pretty much everybody who did it did fine. Problem 4, I noticed that a lot of you did manage to find the 3-state DFA. A number of you didn't show the work with the table filling algorithm and just drew the DFA, so I took off points for that. I've also noticed that some of you in your final DFA doesn't actually contain information about the accepting state or starting state on it, and that's kind of useful information when you're providing an automata. Problem 5, most of you did fairly all right. I did see a few cases where you might not have indicated when this thing should either accept or reject, which is probably the most important part of your Turing machine, but that should be fine anyway, if you've got the general description of how the tape is behaving and whatnot. Problem 6, I think almost all of you got this right. A few of you forgot that the problem also asks for why it might be a poor design choice to have infinite looping behavior. But I don't think too many people actually got like a wrong Turing machine. But yeah, that would be the frequently made mistakes.
Mm-hmm. Thanks, James. That was great. Before I move on and start to talking about wrapping up the time complexity discussion we started, anybody has got any questions about homework 6? What we run through now and what they have been told on Osbo? Any quick questions? All right, it looks like it's all clear. So the solution had been always there. So make sure that you take a look. All right, complexity theory. These are going to be a couple of slides now that are not going to be completely new. We have seen them and then I bring them up just to refresh our memory and then have a continuity in our discussion. So note takers, this is not a new slide, so you can relax and just take a look at what it was before. So complexity theory is about investigation of resources required for solving problems that are decidable. We have Turing machines that's going to decide it, and we are interested in knowing how much time, how much memory, and some other resources it would take. And that is what the area of complexity theory is busy with. And it is a big area, and there's lots of things that happen in there, and it's a course on its own. We just wanted to get an introduction into, out of these possibly three things, and we don't touch even anything about memory or space complexity, but just time. And so this is lecture 3 on this series, and we had seen the first time how to measure time and introduce some notations. And last time we looked at how to classify problems according to amount of time needed. And then there was some open problem that I told you who we ended up with. And so for that classification of problems, I said we'll build our tents big enough so that we won't worry about smallish things, smallish when it is in the sense of complexity theory. And I also want to remind a couple of classes. So there were two big classes we defined. I wanted us to remember them, the definitions for them. And so let me do that. Another place where things have been said before, another place to just relax and watch these slides now, because they have been there before, except that I might have, in some places, pulled one box and pulled another box from another slide so that they come together, like this one, for example. But maybe go ahead, take a note on this one. So we know that we define the class. And the way we are doing in this class, and the course, the entire course is called Automata in Formal Languages. So everything is said in terms of languages, including what we do now in this complexity theory. The way we think about problems is we turn them into language, and so they become membership problems and then things formulated around language, right? So we are now defining a time complexity class, and we gave it this name, time Tn, to the collection of all languages that are decidable by an order of Tn time. So we now know what the big O notation is. By the way, homework 8, the last two questions have got a little bit about notation. One of them, of the two problems, one of them. Of the two last problems, one of them deals about these notations, and we will say true or false for certain expressions, right? So there are languages that, for languages that are decidable by order of Tn time language, we will call that class time Tn. That was one class. Complexity class, we call it time Tn, and so we have a Tn. T of n could be here, order of n. T of n could, or just n, because I've got the big O outside. Or it could be n squared, so I've got all quadratic time algorithms, all cubic time, and so on, right? So I have the Tn to tell me what time it is taking, and then we put all problems, all languages that could be polynomial in one big class, and we called it P, nice P. So P is the union of all k's. K is 1, 2, 3, 4, we can go on like that, and they are all the same. The difference between them, for the purpose we have, is not big enough to warrant to be given a different name. And so our big tent now is P, and it has got all the collection, all the union of algorithms or languages that can be decided by Turing machines that have got time to nk. And K was not so very important for us. And we saw what the significance of P is. We say P is, practical problems belong there. They are equivalently represented by Turing machines that do not change, vary very much from one another, and so on. So we said a couple points about the significance of P. And so by having to put them together and looking at the growth rate, and so compared to exponential functions, for example, these ones grow at a lower rate. And so to put them in one place, something like, for example, a cubic algorithm and a linear time algorithm is okay, because compared to exponential, the growth rate is not that big. And so we have got that class, and we call this class P. The other tent we built was called NP. And this was an interesting class. This was an interesting class because we said, okay, there are problems for, we will, not be able to find a polynomial time algorithm probably, but we can, if it is kind of difficult and we might need an exponential time algorithm to decide it. But if somebody gives me the problem and also a certificate of some kind, a check, can I then verify it in polynomial time? Can I know whether what you've given me now as a solution does in fact is a solution? Can I verify that in polynomial time? When I do that, then we will call that class NP. And so we needed a definition first, and that definition was a verifier. A verifier for a language is another algorithm, a V, where it would accept the input and the certificate for some string A, and then it would verify this A in polynomial time. And so that language is now called this is a definition for a polynomially verifiable language. And then the class of language that have polynomial time verifiers is called NP. So that's the second part. So I did this mistake last time also. The first definition is just a language. That language is called polynomially verifiable. And now comes the class of languages. That class of language for which we have polynomial time verifiers is called NP. But we also saw an alternative definition for NP, and that definition was around a time, just like we did for the polynomial time, the P, the class P, and we defined it as a union of things that are called in time n to the k. We did n to the k was, whatever it could be, and the union was called P. We could do something similar, and except that now the time would be prefixed with an n. The n there is for non-determinism. So the definition I gave you in terms of a verifier doesn't talk about anything about non-determinism. It just said that if I have, given you a problem and also a certificate for it, can you verify it in polynomial time? That was how it was posed. An alternative way and an equivalent way to say it is there a non-deterministic Turing machine that would decide this one in polynomial time? In that sense, then, we could call this class n time t of n, just like we did time t of n. When it was deterministic, we don't put a d in front of it. Now, when it is non-deterministic, we put an n in front of it. And now what we say is we will call this class, it's a class decided by a polynomial time non-deterministic Turing machine. And so the theorem was a language is in NP, the way we verified it, we defined it earlier, if and only if it is decided by some non-deterministic polynomial time Turing machine. This one has got a detail. By the way, for the purpose I have, for our introduction to complexity theory and time complexity, none of the discussions we have had so far involved showing proofs. And so that's intentional. I just wanted you to get some general ideas and know the basic things, not necessarily to prove them. We've been busy proving things all the way from chapter 1 to chapter 5 in the book. This is the only time I'm relieving you of having to show. But the results that is shown in this green box here, in fact, we are equipped, we could solve it if we needed to, if we had time, we could solve it. But the result says we call a language would be an NP if it could be decided by a non-deterministic polynomial Turing machine. So they are equivalent. Verifiable thing in polynomial time means I have a polynomial time non-deterministic algorithm that would decide it, or Turing machine that would decide it. And so we call this class n time, and we take the union of this, and we call that class NP. That's why it's now called a corollary. The NP we defined earlier in the previous slide, slide 8, is the same class as this one, and so they are equivalent. Now, this is the place where I left you last time. This is the place where I said, if you want to make a lot of money, solve this problem. It's an open one. Nobody knows the answer. And so the idea, first the yellow box is telling us what these classes signify, what they really mean when they are reinterpreted. P is the class of language for which membership can be decided quickly. By quickly, we mean polynomial. NP is the class of language for which membership can be verified quickly. By quickly, we mean polynomial. These are the two classes. And the world is either the egg-shaped thing on the left or this kind of circlish thing on the right. Either P is contained within NP and they are not equal, or they just collapse and they are equal. And whether the truth is the left or the right is unknown. It's an open question. And it is the greatest unsolved problem in theoretical computer science. And so I left you here, and we are going to now, as I told you, see a little bit of a positive news or something that would get us have a handle on this. So one of the most important advances on this P versus NP question came in the early 1970s with the work of Stephen Cook and Leonid Levin, and then there is a result. I will conclude this discussion, in fact, with their result theorem, Cook-Levin theorem. When you see these sort of things, you may run into these sort of things. You might have heard other examples in your textbooks and so on. Sometimes you would see a couple of names put together with a hyphen like this, and they might have collaborated. They might have written a paper together. They might have shown this result for the first time, and so they are colleagues and collaborators of some kind. And sometimes you would see things like this, where things are independently discovered by two people at about the same time. And so the credit goes to both of them is what people mean. This is the case here. So Cook and Levin did not collaborate on coming up with this result. They just discovered this thing independently. And I'll tell you what that theorem is, the significance of it, when we finish this one 4 or 5 slides later today. And so the Cook-Levin theorem is one of the advances we have had on the P versus NP question. What did they do? They discovered certain problems in NP whose individual complexity is related to that of the entire class. So when you think about now, I ask you, well, not I didn't ask you, but there is an open question that says, is P equal to NP? And I told you it is unresolved. And so if you think about showing about the equivalence of two classes or the inequality, then it's a difficult problem. That's why we don't have the mathematics for it to show it one way or the other. So it is a difficult problem, but it might, even if you haven't thought about it, you might be overwhelmed because you've got classes. You've got one class and another class to show whether they are the same or not. And so there are many members in each one of these. So the way to go about it itself could be overwhelming. And so the reason what this result is significant, and I haven't told you what the theorem is, but with the significance of it is that they have identified problems within NP that say they kind of captured the essence of it. If you decide one way or another about the complexity of these problems, then you can say something about the entire class. And so they are representatives, or they are the core. They are the ones that would, stand out in the class to show their intricately related complexity of themselves with the rest of the class. And those problems are knowing something like that will be significant. So that's what they did. So if a polynomial time now algorithm exists for any one of these problems, then all problems in NP would be polynomial time solvable. These problems are called NP-complete. Your Magic the Gathering question on homework 7, the last one, if you read the paper that is behind it, you have given your own answer and you were not asked to show anything mathematical or anything like that there. You were asked about something, the possibility and to give a reasoning around it. But the title of the paper that you were asked to do has got the word complete in it. So that it shows up in different places. But the most place I have seen it being associated with is this NP, being NP complete. So NP complete problems are those problems in NP whose complexity is intricately related with the rest of the class, which means that showing that any one of them is polynomial time solvable would mean the rest of the class is, everything in the class is polynomial time solvable. That's what they discovered. Okay, so the importance of NP completeness is double-sided. It is important in theory, and it's also important in practice. Let me start with the theoretical side. I told you the world where the P versus NP question would go. It was the egg-shaped one, P is not equal to NP, or it was the circle-ish type one, P is equal to NP. If you happen to be in one of these two camps, you would benefit from knowing NP completeness. Suppose you are on the first, which is where the majority of the people are. Well, actually, I haven't counted, but I think that is what the consensus is mostly, I think, for research people who are serious about this one. And they are also kind of equipped with what we know now, right? So those people would think P is not equal to NP. It's a conjecture that's accepted by many. So a researcher trying to show P is not equal to NP may just focus on an NP-complete problem. Because if any problem in NP requires more than polynomial time, an NP-complete problem will do. And so that's what they would focus. And a researcher on this other camp attempting to prove that P and NP are equal, just got one thing to do. Instead of showing the entire class now, they have to just come up with a polynomial time algorithm for one NP-complete problem, and then they are done. Because now they can argue that the two classes are equal because the hardest ones of all, the ones that are representative, I have found a polynomial algorithm for it. Every now and then there was some news that would come up and then just to be found that it was not true, and people would actually attempt that. There are people who very, very seriously spend a lot of time in writing, like 50, 60 pages long proofs for one one NP complete problem to give a polynomial time algorithm for it to argue that then P is equal to NP. That is the theoretical side, the theoretical significance of NP completeness. On the practical side, it is a way to show that we should not be wasting our times. There will be problems, and there are plenty, including many of the problems that people in research, algorithmic research like myself, would be busy with. Most of the problems, unfortunately, turn out to be NP-complete problems. If then you have encountered a new problem and you take the time, if nobody has shown it before, that the problem is NP-complete, then you relieve yourself and a number of other colleagues big trouble. They would be wasting their time trying to come up with an algorithm that doesn't exist, polynomial time algorithm. And so by showing that it's NP-completeness, you save time by giving this argument that there is a very strong evidence for this problem to be non-polynomial, that there isn't any polynomial algorithm for it because you have shown it to be NP-complete. So taking the time to show a problem is NP-complete means that you have provided an evidence that is strongly in favor of the non-existence of a polynomial time algorithm. I'm not sure if I've said that clearly enough, but showing that NP-complete means the problem is very unlikely to have a polynomial time algorithm. So there is a practical benefit to it. Okay, so I'm going to get to these NP-complete problems and give you a couple examples. Now, I want to take you back to what we did with these decidability and undecidability problems. We did do something similar, like what we are going to do now. I'm speaking ahead of myself now, and I'll try to tell you how we go about showing how problems are NP-complete. But in this undecidable problems also, there was a time when we needed to show the first undecidable problem, and that was ATM. And you remember what we did with diagonalization and things like that. Much like that, we want to now know the first NP-complete problem that we can think about, and then I'll show you what we will do to show other problems are NP-complete. And that would require me to define a few things. And so I've plugged in a few definitions from the book. And the problem we are going to introduce now has to do with doing something about Boolean operations and some expressions that are formulated around Boolean. So this is like some preliminary definitions for a few things that we need to introduce our first NP-complete problem. And that problem is called satisfiability problem. And so we have variables that are Boolean. That means they can take values that are true or false. True or false, we could also use 1 and 0, and the Boolean expressions are made up with operations like Boolean expressions are made up of operations like or, and not, and we actually don't have others. The other can come by having to do with working with just and, or, and not. That's it. And so you know this from your previous knowledge, and probably you also know how to denote them. So an and is denoted with this kind of inverted V, and then an or is like a V, and then the note is like the negation. These are the symbols we use. And so we know what to do when things are and. Anything ended with a 0 is a 0, anything. And if we have both of the variables associated in a Boolean expression are 1, then the end is a 1. And we know what to do when it's an or, it's the other way around. So if you have 1, 1, it's enough for an or expression to be a 1. And the negation of a 0 is a 1, and the negation of a 1 is a 0. Okay, definition. This is just a reminder, things that you know. And a Boolean formula then is an expression involving Boolean variables and operations. Like, for example, here is one Boolean formula that says phi equals to x bar and y, or, and I've got on the other one, x and z bar. So this is called a Boolean formula. And so now you're asked this question. If there is an assignment, a 0, 1, 0, x will take a 0, y, 1, y will take a 1, or the other way around, or things like that, where you would have to give, given a Boolean formula, you've got some assignment to these variables, such that the whole thing would equate to 1, then that assignment, that problem is said to be satisfied then. That means it equated to a 1, to a true. And the satisfiability problem then is to test whether a Boolean formula is satisfiable. So I've got phi is a Boolean formula, is it satisfiable? That is the satisfiability problem, and we'll call it SAT. And so the result we have, the first problem we know is NP-complete, is this thing called SAT. And SAT will be in polynomial time solvable. It will be in P if and only if P and NP are equal. So we have introduced the first NP-complete problem. So the way now that we know at least one, the way we will go about showing other problems to be NP-complete. So we have now just introduced our first NP-complete problem. For other problems, to show that they are also NP-complete is the way we will do that. The method we will use for that one is something that we are already introduced to when we talked about undecidability. We had something called reducibility there. We reduced one undecidable problem to another problem, and we argued that the new problem now is undecidable. Why? Because if it were decidable, the original would have been undecidable. So if I have now known a certain problem is NP-complete, and I have reduced it to a new problem, then the new problem is also NP-complete, I would argue. Except that now I will be careful on how the reduction is done. And that is what polynomial time reducibility means. And so now we had mapping reducibility last time. This time we are going to qualify it even further by requiring that that reduction is done in polynomial time. So we have first a definition for a function, when to call it polynomial time computable. That is when you have a Turing machine that computes it in polynomial time. That's what it is, basically. We don't need anything more than that. And if we have a mapping reducible, just like we did when we discussed 2 or 3 weeks or lectures ago, when we looked at, and you remember this figure, when we reduced one problem to another, and we call that one mapping reducibility to show that there is a one-to-one mapping between an instance of A to an instance of B, everything in A mapped to everything inside B, and everything outside A mapped to outside B, that type of mapping, we call that mapping reducibility, we call that function. When that function now is polynomial time computable, then the reduction will be called polynomial time reduction from A to B. So now we have this result that says, if I have a language A and I could reduce it to B in polynomial time, now we've got that notation. Last time when we were discussing about mapping reducibility, we called it just M because it was mapping reducibility. Now we call it P because it is polynomial time reducible. If A is polynomial time reducible to B and B is in P, that means it is polynomial time, then A is also in P, obviously, right? I just did the mapping in polynomial time. I could solve P in polynomial time, therefore I can solve A in polynomial time. That will be the significance. But for the kind of thing that we see, and we said Cook and Levin discovered, we will need something called NP-completeness. These are the problems that are at the heart of the class NP. And so what do they have to satisfy for them to earn this privilege of being called the representative of that class? If anything is polynomial for one of these, then the whole class would collapse. What do they have to satisfy to get that distinction? Well, they have to be in P. So any language to be called NP-complete, it has to be in P. Fair enough, that's very obvious. The other thing it has to satisfy is that every A in NP is polynomially reducible to it. Then it's why it's called NP-complete. We have that definition. Now with this definition, if a language B then is NP-complete and B is in P, the one that's NP-complete happens to be in P, then we got an answer for the first question that we had, whether P is equal to NP, then it will be affirmatively answered. P will be equal to NP because now I can go solve every problem in NP in polynomial time also, and that will be the result of this theorem. But this is not what we think the truth is. The truth is the other way around, that they are not equal. So we've got this more important result that says if B is NP-complete, and I can reduce B in polynomial time to a new problem C, for C which is in NP, then C is NP-complete. And this is the recipe for us to show how NP-complete problems are grown. So the first one, the satisfiability problem, we have to find some other way. We just introduced what the problem is, but for everything else from then on, then we have to find a way to get this reduction from B to C to show where B is an NP-complete problem to a problem C, where C is in NP, to show that C is NP-complete. And so what Cook and Levin did, and the reason that they got credit, is they showed SAT to be NP-complete. And the way they did it is shown in 2 or 3 pages long proof in the book now. You don't need to do, but it is called the Tableau method. It's just much like the diagonalization method, well, painstakingly going through everything you have to check. This one also does that, basically looking at all the configurations and things like that. It's called the Tableau method. You don't need to know it. But once we have one NP-complete established, like this SAT, then all additional problems that are also NP-complete can be shown by polynomial time reduction, like the theorem I showed you in the previous slide. That is the more important thing I want you to know. You don't have to necessarily know how to do these reductions. It would be beyond the scope of this course, but this is how people go about showing NP-complete results. And so I'm going to finish, I know it's time, to finish by just giving you this slide. It will be there. So you just have some names of problems that are NP-complete. I have definitions of what the problems are and how they are reduced to show that NP-complete is not something we want to know. But I know it has been 11, and I know that you've got to go to class. Thank you for your patience if you are about to leave. But let me just encourage you to just take 30 seconds to look at this slide now to know at least 4 examples. If somebody asks you, give me examples of NP-complete problems, you can give them these names. So the definitions of what these problems are is given there. And I think for some of you who are familiar with some graph problems, you would immediately see them. In fact, 1 or 2 of them were introduced in some other class before. But this is where I wanted to stop. We have finished. And on Wednesday, we will do the review of the class, and I will see everybody then. If you have questions, that would be a good time to ask me. I'm not going to pretend as if I have time now for people to invite questions, but Wednesday will be a great time to ask questions if you have. Okay, I'll stop here. We'll see you next time.